All right, so far we've been talking about the crypto economy of mining and about basically how to keep the rate of proposals down, but how we keep it up. But we have not talked about consensus itself yet. So how do we do it? Okay, so the basic idea is simple. A miner broadcasts the proposed block, and the block includes a hash to the latest block known to the miner. When another node receives proposed block, it would verify several things. It would verify that the proof of the crypto puzzle solution is valid by calculating one hash and comparing to the target. It would check that each transaction in the block is valid using business logic. And it would also check that the hash pointer is valid, of course, to the previous block. And then if all those conditions are satisfied, it will append the new block to the local copy of the blockchain. The problem, of course, and this is the problem of consensus, is that local copies may diverge. How? Because of lost messages, but also because competing blocks arrive in a reverse order. Imagine that two blocks were produced, blocks A and B were produced almost the same time. Then one node may receive first A and then B, and another node may receive first B and then A. And usually what happens is that, like, okay, it doesn't matter how exactly we do the order. The problem is that locally, a node is not able to determine the correct order between A and B. So the probability of those bad scenarios depend on the network, but they definitely occur. So this is what the consensus problem is solving, right? And this is the critical part. The consensus is resolved by conflict resolution rules. If the proposed chain is longer than the current local copy, then we abandon the local copy and replace it with the local chain that's coming from the network. If the new chain, if the proposed, if what I receive from the network is the same length or shorter than what I already have, I do not replace, I ignore it. So it's called the longest chain rule. And that's the conflict resolution rule in Bitcoin. So why does it solve consensus? It provides probabilistic convergence over time when using the longest chain for conflict resolution. So we'll see an example in the next slide. So it means that blocks the blocks are non-final. So when the block, suppose the block is accepted. And of course, all the transactions in this block are included. So, and then maybe the services are rendered. And then sometime later, a new block comes, and then another new block comes, competing with the current block. So we throw away the current block and replace it with the longer chain. That means that we do not converge. We put a block in the chain, but we don't know if it's final yet. Maybe it will be replaced in the future. How do we know? Well, we don't. We don't know for sure. The good thing is that the probability of a block being non-final decreases exponentially with the number of later blocks stored on the chain. So if this is the latest blocks, if this is the very latest block which I just appended to the chain, it's not unlikely that the block will be replaced in the future. However, if I get another block on top of this one, that decreases the probability that the block will be replaced. If I get 2 blocks later, the probability gets exponentially smaller and smaller. And it never, theoretically speaking, it never reaches 0. It halves, but it never reaches 0. But of course it becomes like, it can become as small as we want. Okay, so when do we declare a victory? When do we say, okay, the probability of replacement in the future becomes so small that we can say it's final? Because that question is important, because we need to know when we can effectively start rendering the services based on included transactions. So Bitcoin consider the standard Bitcoin clients declares victory after 6 blocks. So it's enough the block with the transaction is included, 5 more blocks. It says, okay, now let's say that the transaction is final. Why 6 blocks? It's totally a random number. It could be 5, it could be 7. Just 6 is good. It's big enough for the, probability to the 6 is small enough so we can say it's final. So, okay, so 6 blocks. On average, we say it takes 10 minutes to mine 1 block. So 6 blocks means 1 hour. It's not too bad for most purposes, but sometimes, like when you deal with large-scale vendors like Amazon, Amazon.com would prioritize transactional throughput. So 1 hour may be a lot of time for Amazon.com. So sometimes vendors prefer to risk losing the money, but shipping the services earlier. That happens. So the interesting part again is that there is a proof that, like in a large-scale system, for a period of time, so what happens is that there is a local copy. Every node maintains a local copy of the chain. So the prefix of the local copy is considered to be stable because it's like long enough in the past, right? But the suffix, the most recent blocks, those may still change, right? So then the chain grows and the prefix grows, right? So the stable part grows over time. And if transaction ever stop coming, there would be eventual conversions. Everyone would end up with the same chain. Okay, here's a graphical illustration. So this is like the common prefix. Blocks 0, 1, 2, and well, okay. The participants, the nodes, actually don't know that it's the common prefix. They don't know the situation on other nodes. But we, as observers of all nodes of the system, can observe this is a common prefix. All right. So, and at this point, there are competing proposals of block number 3. They both build on block number 2, but they're different proposals. And they're proposed at around the same time. So there is a split in the network. Some nodes would temporarily accept branch 1, the first version of block 3. Some nodes would temporarily accept the second version of block 3. So there is a split. Okay, what happens next? The network, let's say half of the part of the network, would continue mining on top of branch 1. The other part of the network would continue mining on top of branch 2. So now there is a competition between the 2 branches. Okay, so let's say that the 2 versions of block 4 were also mined at around the same time. In this case, the split continues. And there is a group of miners mining on top of the first version of block 4, and there is a group of miners mining on top of the second version of block 4. However, due to the variance, and that's very important, like there is, we said 10 minutes on average, but in reality there is a distribution, right? So it's very unlikely that the two blocks would be found at the same time. And due to the variance, one group, one branch will find a block faster than the other branch. And when miners receive the valid blocks from a longer branch, they just throw away their own local branch. So, in this case, if branch 1 finds block 5 and branch 2, and there is enough time to propagate block 5 to all the miners also in branch 2, then all the miners maintaining branch 2 will just throw away their branch and adopt this branch because it's longer. So is it clear how it works? Okay. I'm just continuing with Bitcoin. More information on Bitcoin. So far we've covered consensus in Bitcoin, which was a heavy topic, right? Now let's talk about other aspects of Bitcoin. The Merkle tree. I briefly mentioned it. Now I'm going to go a bit deeper. First, how do we build a Merkle tree? We set transactions are in the leaves. Then we take a hash of each transaction, the next level of the Merkle tree. Then we take those two hashes and come it would be hash 0, 1. And similarly, we take hash 2 and hash 3 and compute hash 2, 3. The next level of the Merkle tree. Then the next level of the Merkle tree, until we finally compute the root hash of the tree, which is a combination of the hashes from the previous level. Okay, so this is how it's built. But why are we doing that? Well, again, one purpose is the verification of correctness, right? Data integrity. That's a clear purpose. However, to this end, we didn't need to build a tree. We could have taken a list of transactions. We could have computed the hash of the list and used that hash for integrity. So it doesn't answer the question why we build a tree. So the reason, the main operation for which Merkle tree is needed is what's called simple payment verification. So in Bitcoin, there are what's called full nodes and lightweight nodes. Full nodes maintain the entire ledger. Lightweight nodes don't have enough resources. Lightweight nodes have they could be mobile devices. They only have, say, headers of transactions or blocks. They don't maintain the bodies of blocks, only the headers, because they don't have the space. And the headers are much shorter than the bodies. Okay, so then they don't have information. So for example, if Alice send some transfer, send some funds to Bob, how would Alice know that the transaction is included? How Bob would know that the transaction is included? Normally, you would have access to the transaction, but if you are a lightweight node, if Alice and Bob both maintain a lightweight node, they wouldn't know. So what can they do? How can they verify the inclusion of transactions in that case? Well, what they do is they send a request to a full node that they know. But the question, can they trust the full node? So this is where the Merkle tree comes into picture. So it's possible to create what's called a Merkle tree, a Merkle proof. Merkle proof is a proof of inclusion of a transaction. So let's see how can we efficiently verify inclusion of a transaction in a compact way. Let's say we want to verify inclusion of transaction 3. So we don't have all transactions. We only have which is included in the header, and we have transaction. How can we prove that transaction 3 is included in that particular block? Well, if we have transaction 3, we can compute its hash. Now, if we also have hash 2, we can compute hash 3. We can compute hash 2 free. And if we have hash 0, 1, then together with hash 2 free, we can compute the root hash and verify that this is the correct root hash. In order to do the verification, we need the following. We need hash 0, 1, hash 2, and transaction 3, which we have. We don't need the other information in the tree. We don't need tx2, we don't need tx1, we don't need tx0. We don't need those hashes. So if we have hash 2 and hash 0, 1, we can verify the inclusion of transaction 3 in the root hash. And it's very difficult to falsify, right? Because of the cryptographic properties of the hash function. So what happens is that the full node can send the lightweight nodes, like Alice and Bob in our scenario, can send just the proof, not the entire information in the block, only the Merkle proof. And that would be enough for Alice and Bob to verify the inclusion of the transaction. On the other hand, Merkle tree is not a search tree. So if you want to search transaction or data in the block, for that purpose, you wouldn't be using the Merkle tree. There is another reason, another advantage of using Merkle tree. In Merkle tree, spent transactions can be pruned in the local copy, leaving only the necessary intermediate nodes to save space. What do I mean by that? Spent transaction means that like it's not UTXOs any longer. It's TXOs that have been spent. So imagine that all the outputs of transaction 0 have already been spent. In this case, we are not interested in transaction 0 any longer for that block. So we don't need to keep it in the copy, we keep its hash, right? We can prune it from the tree and save some space. And imagine that the outputs of both transactions have been spent. Okay. In this case, we don't need anything here, right? So this way we can save space in the storage, but of course someone would still need to keep full track of the ledger. So Some nodes would still continue keeping the entire ledger, but some nodes would keep an abridged version. So that's the idea of the Merkle tree. Now, another point is about data manipulation and queries, or another aspect of blockchain, right? So far, we've been talking about how to update the ledger, but what about reading the ledger? So the ledger in Bitcoin is publicly available. There is no access control whatsoever. And not only this is further facilitated by services for querying the ledger, such as Blockchair. So there are some web services whose purpose is only to provide a window into larger ledgers, right? So they extract information about individual blocks and transactions in the ledger. And in practice, a copy is held by many users. And users are encouraged to download and run a verification. So because of this, this transparency contributes to better integrity of the data. So this transparency is definitely a boon for data integrity, but it's a challenge, of course, for privacy, because public keys are used as user identities, so it's not real identities. And a key can serve as a pseudonym. But the main, and as we mentioned, is user should use a different key for each transaction. The main threat comes from analyzing the history of transaction and linking them together. So we'll talk specifically about this topic when covering the Monero cryptocurrency that improves over Bitcoin in that respect. So tamper resistance is mostly a good thing, but the problem with tamper resistance is it's difficult to compact the ledger or prune the history. And let's look at what happens with the size of the Bitcoin ledger. Okay, it's from 2023, now it's bigger, of course. So it's growing. Half a terabyte is not too big, of course, today, but it's sizable, right? And the curve is linear. So up until a certain point, it was small, measure in small number of gigabytes, but now it's about a terabyte. It grows in a linear fashion. So it's not too bad. It's not too big. Again, the thing is that the transactions, financial transactions, individual transactions are very short. But over time, it accumulates. And it can never be compacted. So that's a challenge. Okay, let's talk about the layer, the business layer, the smart contract layer in Bitcoin. It's rather primitive compared to the smart contract layer in later systems, but still it's interesting because it was first. So the output and the input have some scripts attached to them. The output of a transaction additionally includes a verification script, which would represent the conditions under which the output can be redeemed, or in other words, included as the input in a later transaction. And a typical script in Bitcoin would look like this output can be redeemed by a public key that hashes to a certain value, along with the signature from the key owner. And similarly, there is a redeeming script attached to the input. So both scripts are executed for the purpose of verification. And not only by the owners, but also by everyone verifying the transaction. The script language includes an order of 200 different commands. The main focus of the script language is support for cryptographic primitives. However, it's an ad hoc language, right? So there is no even like a description of what can be achieved with it. It's definitely not a Turing complete language. There are a lot of things that you cannot do. You cannot do conditional statements, you cannot do loops, and many other things. So it's rather primitive. But it includes some efficient implementation of cryptographic primitives with focus on signatures and hashes. Now, we are going to spend a lot of time talking about security. So I don't want to talk too much about it now. However, there is this major classical problem of double spending that I do want to discuss. So double spending is again due to the fact that convergence of blocks in Bitcoin is probabilistic and only eventual, right? So for a period of time, there could be two versions of the same block. So imagine that there is a real chain. Okay, first of all, there are two transactions, A and B, and both transactions are transferring exactly the same UTXO to two different users, right? So it's a double spending. Now, there are two versions of the chain. First it starts with like a real chain, and in the real chain, in block number 10, there is transaction A. Okay? So the attacker, whoever transferred 1 Bitcoin to the first merchant would get some services after a while. Okay. And in parallel, in secret, the attacker built an alternative chain. And it would make sure that the alternative chain is longer than the current chain. Okay, so after the services are rendered, the attacker would disclose the secret chain to everyone. And at this point, the attacker's chain would replace the chain so far, and the secret chain, the attacker's chain, would include a different version of block N with transaction B included instead of transaction A. At this point, the attacker would get some benefit due to transferring 1 Bitcoin to merchant 2. So the attacker gets double benefit from the same fund, from the same UTXO. And that's called double spending. So this is like the classical attack in Bitcoin and similar systems, especially systems based on proof of work. It's also called a 51% attack because in order to launch the attack, the attacker would need to overcome the current chain by proposing a longer chain. And to do that, the attacker needs significant computational power, at least 51% of the network. Now let's talk a bit about limitations of Bitcoin. So in what sense Bitcoin could be improved, and it is improved by later systems? First of all, it's only cryptocurrency. It doesn't support applications. So each application requires a new platform. And this is why we came to have Namecoin, Timecoin, Surecoin, and so on. Second problem with Bitcoin, the block time is 10 minutes. So it's not as fast as, say, Visa transaction. So normally, like you are paying for your services with a credit card, you don't want to wait for 10 minutes. And also slow confirmation time, right? So maybe 1 hour for 6 confirmation, after which, it could, so you'll have to say you're paying for your services, you gave your credit card, now you need to wait for 1 hour before they come back and say, yes, your transaction has been approved. It's too long. Next problem is due to forks. What are forks? Forks is a bit similar to branches. So previously we saw a scenario with 2 different branches in Bitcoin, right? Now, forks is the case when there are updates to the configuration or to the code of the system. So Bitcoin, for example, rolls up new updates, and some users like the updates, some users don't like the updates. So you don't have to update your client, right? Now you have a situation where, like in a single system, there are users running one version, and the older version, and the users running the newer version. And the 2 versions are not compatible, right? So we have a partition. That's a fork. Another case of a fork is, say, the size of the block, right? So the size of the block is a constant subject of debates in cryptocurrencies. And suppose some users adopt new size of block, some users are conservative, continue with the old size. Again, we have a fork. So soft forks means that the newer version can still work with the older version. So users who do not update cannot work with the new version, but users who update can work with both versions. That's a soft fork. Hard fork means that the new version is not compatible with the old version, so it's complete partition. There is another related problem and another reason for fork creation. There have been some well-known instances where funds were stolen from Bitcoin, right? So a significant amount of funds. And it's not discovered immediately. For example, 1 month later, users discover that over the entire month, significant amount of funds were stolen. What do? We have 2 options. One option is to say, well, and continue. The other option is to roll back to cancel all transactions over the past month. And not just the bad transactions, not just the thefts, all good transactions too. Okay, this way you cancel the theft, but you also cancel the good transactions. Is it a good trade-off? Not clear, right? Not clear if it's a good trade-off or not. Again, there is a debate, and people disagree. Some people roll back, some people do not continue forward. We have a fork. And it's actually funny that a lot of forks were created this way. Those forks usually have some very fancy names, like Bitcoin Gold, right? Sounds very good. It was because of theft. So it's not a good thing. More limitations. So the transaction rate in Bitcoin is only 7 transactions per second. It's not so good. Compare that with Visa, where you have like 2,000 transactions per second on average. And it can even support more than that. So, okay, it depends on the block size, and again, there are a lot of discussions about the block size. Next, Bitcoin uses proof of work. And there is a reason why later systems abandon proof of work and prefer to go for alternatives. So the reasons are, the main reason is that proof of work, it doesn't benefit humanity whatsoever. It benefits the miner. The miner gets the reward, right? But the miner found a solution to the crypto puzzle. Well, that solution is not useful to anyone. And yet, the miner spent significant amount of resources and energy, power, in order to find it. So the environmental impact, it uses, despite the much lower throughput, it uses thousands of times more energy than credit card transactions. And we'll see comparable energy consumption is comparable to a decent-sized country. Like if you take all Bitcoin miners together, they spend as much power as some moderate-sized, well, not India, but moderate-sized countries in Europe. There are also some minor disadvantages related to the bootstrap time for a miner. So, so what happens? Like, suppose new miner wants to join the system, it needs to download the entire ledger and verify it. Well, that process takes days. Okay, so let's see some charts related to energy consumption by country. Okay, it varies across the time, of course, but here it's Austria, Bangladesh, Chile, Bitcoin, Finland, Belgium, Philippines. Right? And this is comparison of energy consumption with Visa. So in Bitcoin, uses maybe like 500 kilowatt per hour for one transaction. While Visa uses less energy for 100,000 transactions. So then that's one reason why later systems were trying to get away from POW. Okay, so what are the alternatives to POW? Let's quickly go over the alternatives, and that will be the last thing for today. So Ethereum switched to proof of stake in 2022. So what is a proof of stake? In proof of stake, validator bids for the right to propose blocks by staking their tokens. And then, after different validators place their bids, a lottery takes place where the probability of being selected as the proposer is proportional to the stake you put. Well, that's definitely much cheaper in terms of the energy consumption. However, it's not a perfect mechanism either, right? So one issue is that if you don't have funds, then you cannot put a stake and you cannot become a proposer. So as a result, the rich may be getting richer, while the poor stay poor. The other problem with proof of stake, the other disadvantage of proof of stake is the issue with deposits, right? So the deposit, after the stake, the deposit is locked, and then it can also be locked for a period of time, right? So there is a question for how long. Should we return? Okay, so should we return the deposit immediately, or should we keep it locked for a period of time? We can keep it locked in order to make sure that not too many attempts, not too many stakes are proposed in parallel. So there are a lot of debates for how long to keep the deposit locked and whether it's a good idea. The next alternatives, well, it's not suitable for every system. is proof of authority. In proof of authority, well, it's only used in consortium blockchain. So there are a few dedicated nodes which can decide together that, like, still not one node, but a few, and they do not necessarily trust each other. But they decide, they make all the decisions in the system. That's a simple one. The next alternative is quite interesting. It's called proof of elapsed time, and it's using the trusted execution environment about which we were talking earlier. So, node, say a miner, or a node who wants to become a proposer, would request a waiting time from a function running in the trusted environment. And that function would create some random time and sign it. And now, everyone can place a bid with the shortest wait time produced by the trusted environment would produce the block. So that's the basic idea of it, right? And it's very fast. It can scale to thousands of nodes, and it can be quite energy efficient too. But of course, it requires trusted execution environment, which is expensive and not universally adopted. Yet, this idea of proof of elapsed time is used by Sawtooth, Hyperledger Sawtooth, and it's also used by Solana, which is a popular cryptocurrency. And of course, it means that you need to trust Intel, right? So you assume that Intel cannot be bought to favor some miner or some proposer, right? Okay, more alternatives. There are many more actually. There is order of 30 different alternatives. I'm not covering everything. I'm just giving you some taste of what exists, right? So proof of capacity. Proof of capacity, also known as proof of stake, proof of storage, requires that validator nodes commit hard drive space to increase their chances of producing the next block. So the idea is commit some space on the hard drive, like a deposit, right? So you deposit not only cryptocurrency, you can stake your resources. And the resources could be this space. So that's an interesting idea, again, quite cheap, and used in quite a few storage systems based on blockchain. Okay, so that's the end of the lecture today. Welcoming questions.